So finish off this section on double integrals, and then with whatever time it remains, we can look at the latest homework. Now, first some terminology, but I didn't really need this for the examples, but I want to throw it out there in case it comes up on the homework in this section. So, it's common in double integrals to describe certain regions of being of type 1 or type 2. I guess whether we use Roman numerals or not depends on the textbook. And whether we read type 1 type 2 depends on how you're able to describe it. So if it's type 1, instead of all points where x is between a and b, and then, so at least x has constant limits, and then y is bounded above and below by functions of x. Okay. So if you're able to describe a region as being of type 1, then what that means is the integral over that region, it makes sense to use x for your outer integral because the limits are constant, and then your inner limits for y would just be these upper and lower bounds on y. Okay. And then type 2 is just the other way around. So y is bounded above and below by constants c and d, and then x is bounded below and above by functions of y. So in that case, you would have y being your outer integral and x being your inner one. So integrate. So what you do is first integrate with respect to x, and your limits will be these functions of y. Then you have an outer integral with respect to y with constant limits c and d. Okay. So the goal is, if for certain problems, you may be given a description. You'd like to have this description because then you can just read the limits off the description. But often you may have something that's described in words, and you need to figure out what these lower and upper bounds are in x or y. So if you are not given a region that's described in either one of these forms, then you might wonder, well, how do you know where it should be type 1 or type 2? And so there are certain shapes that you can readily identify as being a type 1 or type 2. So if I draw these, type 1 would be something like this, where you have vertical boundaries, so vertical lines for your left and right boundaries, and then you have some function. It could be a curve, it could be another line. It doesn't matter. But if you have vertical left and right boundaries, then that is type 1. And then type 2 would just be the opposite. If you have horizontal boundaries for your top and bottom, it could be something like this. Maybe it could be a straight line for your left boundary, but it doesn't have to be. So this would be type 2. Okay. So you get the idea from visual. Now I'm going to draw a region that can be either one. if I have something like this, where I have a horizontal, wow, I really had these backwards today, what's wrong with me? Must be because I'm hangry. So I have horizontal, no, I've eaten nothing all day, so horizontal and vertical boundary. And what you have is a situation where, in this case, the right boundary is just a single point, or something like, or if it's upside down, similar idea, something like this, where, and there's different orientations you can try, but the point is, some boundary is collapsed to a single point, and that gives you some leeway. So if I fill in some generic boundaries, so this is x equals a, this line is x equals b. Here we have, I'll just make this y equals c, and then I have y equals g of x up top. So in this case, I'll call, so this is my d. So for this example, the integral over d of whatever function f you have can be written as the integral from a to b. So here I'm giving it type 1 treatment. So your lower boundaries are y equals c, and then we have y equals g of x. Okay. F of xy, dy dx. Now I need to make another assumption about this function g of x. It has to be 1-to-1. So for instance, in other words, it must pass a horizontal line test. So something like this, not allowed. Okay. Because you can still describe it as type 1, but not type 2. So what I want us to work out now is if I want to take this same integral, same region, but I want to describe it as a, okay, so I need to fix this. I need to rewrite this as an integral of type 2. So I need limits in y now, on the outside, and then x on the inside. So can anyone tell me what either one of the y limits should be?
Couldn't you just use y equals c and y equals g of x?
Almost, yeah. C is certainly the lower limit. You do want to use g, but g of x is a function. We need a number. So, but you're on the right track. Let's stick with g here. So not g of x as is. What?
G of a.
Bingo. Yes, g of a. Because the function is, okay, it's 1-to-1, and it has to decrease down to this point. So the highest point, the highest y value you can get is right here at x equals a. All right. So yes, whatever g of a is, so you can go ahead and plug that in to your function, and then you'll get a number, and that'll be your upper limit. Now, limits in x, so now you're going from left to right, and certainly the left boundary would be x equals a, and what will we use for the right limit?
Would it be a function of b?
What?
Would it be a function of b?
No, b itself would not be involved. Yeah, because b would happen to be the upper limit for for y equals c, but not anywhere else. So it cannot be a function of x. It can be a function of y. But what curve describes the right boundary? Just from what's on the board.
Would it be 0?
No. Well, but that only works down here.
Right.
Not for, okay. So, because it's this curve that's the rightmost boundary, but we can't use this description y equals g of x. We can't have a function of x.
I equals G of B. We're just plugging stuff in over here.
Okay, no more random guessing.
C to G.
How would I? Here I have y being a function of x. What would I? If I want to describe this x in terms of y, how do you do that? What's the
The integral.
no
Oh, hang on.
inverse function? G inverse of y. So here we have y equals g of x, which is equivalent to x equals g inverse of y. So for instance, if this was a squaring, this would be square root. If it was exponential, this would be a logarithm. That notion of inverse functions, okay, when did you even see inverse functions? I don't even know.
Trig.
Okay, yeah, because they definitely would come up there. And probably anywhere else. It doesn't even come up. The funny thing is that at another school, when I taught Cal 2, we actually we had a whole section just about inverse functions. And then we could talk about exponential and logarithmic in specific cases. But we may have just stumbled upon a curriculum deficiency. And not the only one, I'm sure. That sometimes you have an equation that's in a certain form, but you need to flip it around. And you can do that with our algebraic manipulations you're already familiar with, because all you're doing is you're just taking this equation and you're isolating x, but that's what you need to do. And now you can express this, and the thing is we did this in a specific example last time. So what I would suggest is the example from last time where I had the integral involving e to the y cubed. In that case, we started with this. That was not doable. Had to change to this. So we did, and it required this kind of inversion. So if you look back at that example, you'll see more concretely what I'm talking about. But now you have a general principle. If you have a region that looks something like this, where you have a one-to-one function, you can do it as type 1 or type 2, whichever one gives you an easier, or in that case, possible integral to do. Is there any questions about this one? Before I forget, let's do the attendance thing. Okay. All right. Okay. All right. So, as I mentioned before, double integrals can be used to compute the volume under a surface. Z equals f of x, y. So this will be another example like that. The difference is it won't be over a rectangle. So it's finding a volume of solid. Here's a common phrase that's used in problems in this kind of class. In the first octant. Now, remember from trig or other courses, well, trig especially, how the xy plane is divided into quadrants. In quadrant 1, 2, 3, and 4. Like quadrant 1 was where x and y are both positive. So now here we're in three-dimensional space. You have x, y, z being positive or negative. So three-dimensional space is divided into 8 regions. So those are octants. Now the strange thing about octants versus quadrants is, I bet if I asked you what were the quadrants 1, 2, 3, and 4, like how are they numbered, you could probably tell me. No one can answer the question for octants because, except for a first octant, x, y, z greater than or equal to 0, if you want to include the axes, textbooks and such have not agreed on how to number octants 2 through 8. So we'll have a share of problems to deal with first octant, and I'll never bring the other ones up because no one can be expected to know what they are.
Does that say volume?
Yes, that says volume. Yeah, I know my penmanship's a little suspect. Whoa. Okay. think I can write my L's better since that's my last initial and all. But, okay. So the first octant, so right away we have these bounds. So that helps describe the domain. And then we also have bounded by these planes. Z is equal to 10 plus x plus y. Z is equal to 2 minus x minus y. And also the surfaces y equals sine x, y equals cosine x. Okay, so if we want to try to visualize what the base of this solid would look like, if we just visualize an x and y. So we're bounded by y equals sine x, which looks like this, and y equals cosine x, looks like this. Now, so I have these boundaries, and just to make it unambiguous, I will also explicitly specify x equals 0 as a boundary. So viewed from above, this is what we're looking at. So x equals 0 makes sense that would be a limit for x. Where do cosine and sine intersect? What's this point right here? Does anyone know? Remember from trig where? Pi over something, but not 2.
Pi over 4?
Yes, it is pi over 4. But we're both equal to square root of 2 over 2. Okay, so in fact, those would be your limits in x. So the volume, so from the picture, we have going from 0 to pi over 4 dx, and then in y, what should those limits be from the picture?
Cosine inverse y. No, wait, I'm using.
Okay, so
Hold that thought.
okay, so we've defined the extent of a domain in x, but now we need to do the same in y. So we need our bottom boundary and our top boundary. Yeah, sine, because between 0 and pi over 4, sine is less. So that's why it's the lower limit. And then cosine. So these limits cover the shaded region right here. So left to right, bottom to top. Okay. Now, what about our boundaries in z? That's going to go in here. That's going to be our integrand. And we have this already solved for z. But we have to make sure that it's, again, larger value minus smaller value. So in fact, I could look at it this way. That if I were to prescribe lower and upper limits in z, keep in mind that x and y, x is between 0 and pi over 4, so pretty small values of x. Y can be between sine and cosine x, and those values are going to be between 0 and 1, and you're subtracting them. So look at these two equations. Which of these will have the larger values?
10 plus x.
Yeah, 10 plus x plus y. Now that's not true in general, but for these x and y values that we have here, yes, this one is the greater one. So you can think of it as smaller value, 2 minus x minus y, up to the larger value, 10 plus x plus y. And then, so actually what I've written here, and I know it's probably premature, well, yeah, it is premature because I cover triple integrals later, but the integral over a three-dimensional region of a function f of x, y, z equals 1 gives you volume, just as the area of a region D would be whatever limits you have in x and y, and your integrand is again 1. So integrating 1 over a region of any kind, one-dimensional, two-dimensional, three-dimensional, gives you the size, length, area, volume of that region. This is even true in single integrals from Cal 2. So the integral from a to b of a function f of x equals 1 is just b minus a. The lengths of, in other words, the size of that interval. So integrating 1 always gives you size. Now, but the thing is, that means your innermost integral is very easy, because when you're integrating 1, what's the value of the integral? It's the difference of the limits. So we can condense this right back to a double integral. And inside here, we're just going to have upper limit minus lower limit. Okay. Now, and for homework purposes or even test purposes, if I give you this double integral, you can just, this is what you would write down. This is your setup. But I just wanted to take a moment to explain, where does that really come from? Why is it this minus this? You can also think of this as integrating 1 over a three-dimensional region. Okay. So now we can simplify this. Sine to cosine. And we get 10 minus 2. So 8x minus a minus x. So 2x. And then 2y. Okay, so now the integral is fully set up and ready to go from there. Actually, these are one of those common mistakes. I've seen too many students not put in parentheses where needed, and then they forget to distribute a minus through something, and then they're heading down the track to Wrongville. And so I've never seen a case where one has too many parentheses. So something to keep in mind. So if we take that and work out the inner integration, which is with respect to y, what are we going to get?
Y squared over 2.
From this?
Get 8y
Yes.
Oh,
Plus 2x y.
x y squared.
I did it backwards.
8y plus, I heard a 2xy plus, y squared. With limits sine and cosine. Because when you're first carrying this out, think, okay, this is a polynomial, this is easy, power rule, blah, blah, blah. And this is where things get ugly, because these are the limits you have to plug in now. In this case, you're plugging them in for y. So you're going to get 8 cosine x plus 2x cosine x plus cosine squared x from the upper limit minus, same thing for the lower limit being sine x, 8 sine x plus 2x sine x plus sine squared x. And we can try to simplify that. Well, not a whole lot we can do really. Since there's 8 cosine minus sine plus 2x cosine x plus sine x minus, okay. Finally, cosine squared minus sine squared. I don't suppose anyone happens to know what cosine squared minus sine squared is. No, it's not 1. I knew somebody was going to say 1.
Well, if it's plus, it's.
If it's plus, then it's 1. Minus, different story. But there is an identity for it. No.
The secant,
One
But-
minus
secant squared, or
Stick to cosine and sine.
okay.
I should probably give up this point that nobody remembers.
one minus
Okay.
sine squared.
Cosine 2x. So it's one of there are three double angle formulas for cosine, and this is one of them. And this is quite helpful, okay, because this part, no problem. You just integrate cosine and sine directly. And now this part, also no problem. But what about this? What will we need to do to integrate something like this? That you have to deal with in Cal 2. What?
Some sort of U substitution.
Not substitution.
We're on fire today.
Yeah.
And I'm any better? I mean, I couldn't even get horizontal vertical straight.
Integration by parts.
Yes,
That's all
integration
I
by
got.
parts, where this would be the u, and either one of these, like you could do them separately, would be the dv. And because then your du would be 1, and you would carry that out from there. Now, due to time, but yeah, I can totally spend the rest of the class doing this, but I had everything to mind. But page 79 to 80 in the notes is where you'll find that. All worked out. Okay. Now, before we get to homework questions, so, all right, and yeah, the final answer is something pretty ugly. Pi squared of 2 over 2 plus 8 squared root of 2 minus 19 halves. Okay. Now, I mentioned before, if you're integrating 1, that gives you area. So for instance, if we have a top half of a unit circle, so radius 1, so this is x squared plus y squared equals 1. If we were to express the area of this, so I'll call this D again. The area of D, so often use this notation, A of D means area of D. I used this last time too. So that would be the double integral of 1 over the region D. But then what would the limits be? Well, so what should, if I want to express this as a region of type 1, so I need limits for x. So this is just a plain old unit circle of radius 1. So what should my limits be in x?
-1 to 1.
Yeah. And then what about y?
It'd be between 0 and pi over 2.
No.
Sorry.
We'd have to take this equation, x squared plus y squared equals 1, and solve it for y. And then, because we're looking at the top half, that says use a positive square root. So it'd be square root of 1 minus y squared. So that's the setup for this integral. And because we're just integrating 1, the inner integral,
I thought we were solving for what?
Yeah, that's,
yep, we are really on fire today.
it's Friday.
Thank goodness. But it's only half over. Yes, we were solving for y, in theory. Okay, so, what? Okay. So now the inner integral is easy. We just take the difference of the limits. So now we have an integral from -1 to 1 of this minus this. So it's a square root of 1 minus x squared. And you might think, okay, how hard an integral can that be? Well, that integral is a pain because you may remember from Cal 2, after doing substitution, integration by parts, you also learned about, hopefully, trigonometric substitutions, which I recall from when I would teach Cal 2 would be among the most painful examples to work through. So the way you would work out this kind of integral, so it's somewhat the opposite of a u substitution. U substitution, you express u as a function of x. With trig substitution, you express x as a function of your new variable, like would be theta. So you make a substitution, in this case, x is equal to sine theta, which is convenient for getting dx. So dx is cosine theta d theta. And the reason why the substitution is chosen is it changes this square root into also cosine theta. So then you can express the integral as from minus pi over 2 to pi over 2 of cosine squared theta d theta. Because you get cosine from here and another cosine from the dx. And you might think, okay, cosine squared looks harmless enough, but it turns out that integral is not straightforward either, because there isn't any convenient u substitution. If this was cosine cubed or over odd power, yeah, that would be easy. But no, you have to use a trig identity, and I'd even bother asking if anyone knows what the trig identity for that is. Okay, probably wasted a few seconds of class time there, but 1 plus cosine 2 theta over 2. And if it was sine squared, it would be 1 minus cosine 2 theta over 2. Finally, this can be done. You can integrate these directly. But the thing is, since for a simple shape like this, the top half of a unit circle, you can get the area by other means. So I bet someone could tell me what the area is without looking at any of this. Because we all know the area of a circle, don't we? Yes, so r is 1 in this case. So, yes, the answer does turn, and if you were to actually work this out, which you could do, that is what you would get, pi over 2. Because the integral of this part, cosine 2 theta, that just turns out to be 0 anyway, so like, what a waste. Okay. And the only reason I'm doing this example, again, to highlight, if you have a problem computing the area of a two-dimensional region, that just means you integrate 1 over a region. Also, these two examples highlight that, unfortunately, those techniques that were taught in Cal 2, you need to bring them back now, at least for homework. Now, again, I'm not going to give something on a test that's going to take you 30 minutes when you have 50 minutes for a test. But these things do come into play. They could pop up on homework, for instance. Okay, so any questions about this one? Of course, when I would teach these in Cal 2, often some of these had to be worked out by completing a square, and I find that nobody would remember that either. Okay. Let's see. This was great about having this job because I couldn't forget any of this stuff if I tried. Yeah, it seems kind of strange because you guys are taking on average 5 classes or so, and if those of you who are math majors, maybe taking 2 or 3 math classes, but then you're having to shift gears to something else like chemistry or English or who knows what, or God forbid CSC 101. And I really dislike that class, but
Just a plethora of information.
yeah. No, I mean I was a computer science major too. That what we have here is not how a programming class should be.
Shots fired.
Okay. Yeah.
You should use that class then.
Okay. Well, okay. Not only have I taught C++ before elsewhere, but we actually briefly contemplated what if we had our own class to fulfill the requirement. And I was told that would not be a good idea because, and I guess because I'm about to fire another shot. So, because if we did that, therefore computer science would be getting fewer credit hours from our students. because we wouldn't require CSE 101 anymore, then they would retaliate by reducing the number of math classes that their students would have to take to try to like even things out. So, yes, that really goes on here.
It's very political.
Yes, it is. So, okay, I better stop. Okay, so what was now I forgot what my point was.
Math. Close.
That's generally the point, but that's kind of why we're here. Oh yeah, but you're taking all different kinds of classes, so then you only get to spend a fraction of your time on this. And how much opportunity is there to really have it sink in? Whereas, I'm spending, the equivalent of a full work week, or well, okay, really more, either up here or helping one of you guys or someone else from whatever class, and so it just you can't help but have it stick. Although my own calculus professor said that the purpose of college is to learn how to learn. So you may not be using these specific things, but if it means you can pick up what you really need, then I guess our mission has been accomplished. But I guess we'll find out. Okay, we have time. Yep. Homework questions like on Lagrange multipliers.
Allow me to just say that I hated that homework with passion.
Even after I cleared.
Well,
Yes.
before.
Okay.
I mean, it was
Okay.
still quite aggravating after, but.
Okay. Yeah. And the thing is, last time I taught this class, I actually had to cut that topic out because we lost some class time. Okay, so this is the 13.9 homework. So does anyone want to?
Number
10?
10.
Okay.
It's 13.9.
Yeah. Okay. Come on. And I'm gonna probably get some angry call from somebody in computer science. Don't put me in that position, okay? Okay, but it's still true. Okay.
No apologies.
Oh, sorry, I went to the wrong thing. Assignment, okay. 13.9, preview. Number 10. Okay, so dimensions of a right circular cylinder of maximum volume, etc. That okay. All right. So okay. Cylinder of maximum volume. Okay. Inscribed in a sphere of radius 11. Okay. Right. Okay. All right. So for something like this, definitely want to visualize this. So the dimensions we're looking for. All right. So find the dimensions, which is the radius and the height. Okay. So we have. something like this. Okay, so here's our radius and here's our height. Okay, so then the objective function is, okay, so it's maximize the volume, which is pi r squared h. But then we need to describe the constraint. So that's going to be inscribed in a sphere, however badly drawn that sphere may be. Wow. Okay. That has a radius of 11. So what's happening here is, since you want the cylinder to entirely fit within the sphere, the question becomes, where does that cylinder actually touch the sphere? So it's these rims right here, but there's actually some contact. So to understand what the constraint would be, it's actually a direct side view would be more helpful. So here's another badly drawn sphere. And here's your cylinder. Okay, so this distance right here, this side is r, and what is this distance going to be?
The radius of the sphere.
Which is 11.
Yes.
You're describing a sphere of radius 11. Okay. All right. Now, so on the one hand, we have our okay. So we have this right here, this distance. Now, there's actually two ways we can express this distance. So what would be one way, based on what we have in the picture, what this distance would be? Almost.
The square root.
Square root of that, yeah. All right, square root of 11 minus r squared. Okay. 11 squared. All right. Since 11 represents the hypotenuse of its right triangle. Okay. We good on that? How else can we describe this distance, though? In terms, because we need to bring the height into it. How does that same segment relate to the height?
It's 1/2 the height.
Yeah, it's h over 2. So now we have square root 11 minus 11 squared minus r squared is h over 2. So now, so there's actually two ways to do this problem, because you could rewrite this as a constraint function g of rh. So in terms of the notation of using the section, this would be like an f of rh, a function we want to maximize. But you can also, and therefore this would be our constraint, and you can solve this by the usual approach of setting the gradient of f, which as partial derivatives with respect to r and h, being equal to Lagrange multiplier lambda times the gradient of g, where you'd also have partial derivatives with respect to r and h. But can anyone tell me what would be another way, not using a Lagrange multiplier, to solve this problem? Something you couldn't always do, but you certainly could do it here. This is actually a calculus 1 thing, where you had to solve max-min problems back then, and you were given some sort of constraint. I could use this equation right here I could solve this for h and eliminate h. So now I have a volume described not as a function of r and h, but only a function of r, and the constraint is already taken into account. So then it's a one-dimensional minimization problem. I don't know why I threw it in here, but maybe if I thought nobody would realize this. That you can just take the derivative with respect to r, set it equal to 0, find the critical number, and so forth, and make sure it's a maximum. So either way, because the problem's not going to know, you're going to fill in an r and an h value, and if it's correct, there you go. So, but it's a good idea to see why you can do it either way, because the only reason that option is here is because this is easy enough to solve for one of the variables, but that isn't always true. Okay. Any questions about that one? Any other one in the last few minutes? I saw a lot of these had a view and example option. This one did not. So I kind of expected to be asked about this one. You guys should get a few minutes early, don't you? Okay, well, but anyone can ask me questions after class too, so, okay, we're done.